All right, then there's chapter 2. Okay, so in chapter 2 we're going to be looking at Kirchoff's junction rule. Let's give it all that room. Basically what that's going to say is if I have a junction, I have these ideal wires coming together at a point. Actually, it doesn't even have to be a point, right? Since these are ideal wires, if I just did this, connected them all to this ideal wire going around, it would be exactly the same because there's no changes going on in that ideal wire. But any place where that entire region where those things connect is the same potential, right? So circuit diagrams are not physical representations of the circuit. They're just ways to represent the circuit in a simplified manner so that you don't have to worry about all the twists and turns and other things that don't really matter but are very important if you're actually trying to fit something into another thing, right? So what this says is that if I have some amount of current coming in, then all the other currents coming out, let's call that 1, and then this one 2, this one 3, this one 4, all the other currents coming out will equal it. And that'll also be true if I have 2 going in. If I have 2 coming in, then the 2 coming into the junction will have to be equal to the amount of current coming out. Basically, that means no charge, no electrons are going to collect right at that spot where everything's connected. Everything's going to keep on flowing through. If you have collections of electrons, you have something called a stray capacitance, and that's actually a problem with your circuit. You usually don't like having those stray capacitances. And so, you try to get rid of those while you're doing this, and hopefully you don't have them, and you don't have to worry about them. If you do, then there'll be some charging at that spot, and you'll have to worry about other things. We'll talk about that kind of charging in the next lecture. But ideally, that doesn't happen. All right, and we won't even talk about it in that context. We'll talk about it in the context We'll talk about that in the context of something you actually want to do with a capacitor. But usually, what people are worried about with capacitances like that are going to be trying to avoid them. Right? You don't want to put those in your circuit unless you really need them. Right? Use capacitance for other things, actually, for resonances and other things that let you learn something about your system. So, we're looking at the junction rule, and it just says what I just said. The total current coming in is the total current leaving a junction. Okay, so this is your total current in, I1 plus I3, let's say. This is your total current coming out, I2 plus I4. And they can be any combination. You just have to keep track of which way the current's going. All right. Some of that we'll have to figure out. So in the last example, we'll end up figuring out what the direction of the current is in one of the branches in some circuit. But usually we're not really worried about that. Okay, usually all we care about is, usually we have a pretty good idea of where everything's going, and we want to figure out just how much is going to branch off this way and how much is going to branch off that way. All right. An important thing to notice, or to note, is this is the only place where you're going to see Gauss's law. And that's a shame, because Gauss's law is a fundamental property of electricity. And basically what it says is that if you have a field, and remember the currents are following fields. If you have a field, then if there's no charges present, if there's no source present, in this case it will be a source, then there's not going to be any additional field coming out or in. So that's basically what this is going to be saying. And in this case, in a circuit, what we're calling a source is going to be a anything that provides a potential, like a battery or something like that. And you could put a battery in right here if you wanted to, and see what happened to all the current coming out. Actually, all the current would have to come out in that case, probably. Well, maybe not. Could be. It would just be another input to this point. So, no, scratch that. You don't. It doesn't necessarily all come out. But if that's your only source of current, it's going to be flowing out of there. And so that's basically the only thing you're going to have as a current source. Well, a capacitor, but that capacitor is only in a transient mode, going between two different modes. And we'll talk a little bit about that on part 8, but we won't try to incorporate that into a huge circuit or anything to really hurt your brain. So we'll just keep that sort of simple and just pretend that sources only come from batteries, okay? Or similar power supplies. So that's Kirchoff's junction rule. That's the first rule of Kirchoff's. I'll put this in a battery, or I'll put this in a circuit for you with a few batteries and a few resistors, and we'll look at basically what happens to a junction as things come out. And we'll see it again in the last example, because the last example will put together the junction rule with the loop rule, which is the subject of the next lecture. All right? Bye.